Yeah, it's 10 a.m. and we can start. First of all, uh, yeah, we finished grading the exam, right? Um, on on Friday. Yeah, on Friday. Right. So the you can see grading, right, in grade scope and the scores, and of course you can see just scores in Blackboard. I also posted my solutions to Blackboard. Then I created quiz number 3, right? And I sent you email about that last night. If you go to the main page of our Blackboard, it's at the very top, right? So and the due day is Wednesday midnight. I like that problem. I remember I had that problem when I was in your shoes, right, as an undergrad student. So I remember that problem. I liked it, and now I decided to give you. But of course, I give you what, 3 days almost to finish this. But actually, that problem which can be solved like in 3 lines only. Right? So it's not that complicated. You just need to think and realize there is a very nice and elegant trick which can be used to solve problems of this type. Okay, so that's about other stuff. And now back to the material. So basically now we need to make in the course, right, in our direction. We have to make a small change in our direction. All right, so up to this point, we basically first we lay down the foundation. Then we introduce an energy approach as a sort of like a shortcut to simplify our lives in terms of complications. So we just added a new set of tools which can be used to analyze problems. Basically, we can say we were still kind of preparing ourselves, right? And now after you prepared all the major quantities, major ideas, right? So now what? Now it's time to start applying them somewhere, right? In some real applications, right? And now it's time to start looking at simple circuits. So basically now we will start making a transition so we can apply all those fundamental ideas, stuff, tools for simple circuits. And as a result, we will start introducing elements, which you can see in circuits like batteries, capacitors, then resistors, and so on, right? All right, so basically from today's class, we will start making the transition. But before we start introducing the first element, let's look at properties of conductors one more time, because now we introduce a new quantity, the electric potential. And so what can we say about the electric potential inside of a conductor in electrostatic equilibrium? Completely logical, reasonable question. And since we will need that additional property, now let's discuss that. So I wrote the title, and now, first of all, let's just refresh the ideas, the major properties of conductors in electrostatic equilibrium. All right. So if I have a piece of a conductor, right? So it's a conductor. Probably I should have written metal. It's easier. All right. And if it's an electrostatic equilibrium, of course, it has tons of free electrons. And then in electrostatic equilibrium, electric field inside of the conductor must be 0 all the time. Right? Then, if this conductor is charged positively or negatively, it doesn't matter. Then, of course, all that excess charge can reside on the external surface, exterior surface only, right? And then another thing, electric field outside of the conductor must be perpendicular to the surface, right? Again, it all happens in the electrostatic equilibrium when electrons are finished doing their job. You remember? Electrons will keep running and running and running, and they will never stop until they will make electric field 0. When electric field 0, they get settled, right? And that's the electrostatic equilibrium. And now what about electric potential? Right? So what about the electric potential? And since we have some information about the electric field, It means that we can get information about the electric potential using bridges which we derived and introduced in the previous lecture and previous recitation class, right? So we just need to use that bridge which allows us to move from the electric field to the electric potential. And that formula, if you remember, okay, let me show that now. We have to move from the electric field to the electric potential, that bridge. And the formula, delta V equals minus integral from some initial point to the final point, E dot ds. So that's the most general form of that formula. Okay, so any initial and any final point can be used. It's basically like universal. So let me pick a completely arbitrary here, for example, that let's say this is my initial point and that is my final point. Completely arbitrary, no restrictions, but inside of the conductor, of course, inside of the conductor, because I want to get information about the electric field inside, electric potential inside of the conductor. And of course, we have to integrate over some path. So let me pick that path, completely arbitrary. You can make it more complicated if you want. And so we need to evaluate this integral. What will be the value of this integral? What will be the answer if we integrate this? What will be the answer? Which function we are integrating? We're integrating electric field inside of the conductor. What do we know about the electric field inside of the conductor? It's zero. You're integrating over the line where the integrand, the function is zero. If you keep integrating zeros, what are you going to get? You're going to get zero, right? So since this is zero, as a result, delta V equals to zero. So as a result, which conclusion can we make about the electric potential? Usually, again, all these students give me these answers, right? But since now it's more complicated to communicate, so usually I play both roles, right? So usually students, if I ask, so what can we say about the electric potential? The usual answer, almost every time, is the electric potential is zero. No, it's a special case. Electric potential will be zero if the conductor is not charged, yes. But in the most general case, and we have to present the general situation, electric potential is constant. Because what are we getting? Delta V equals zero. It means that potential difference equals zero. It just means in the most general situation, we must say that the electric potential inside of the conductor is constant, right? So if it's positively charged, potential can be plus 5 volts, for example. If it's negatively charged, then electric potential can be minus 3 volts. And again, everywhere inside of the conductor, it's constant, all right? So that additional property which we need, electric potential inside of a conductor in the electrostatic equilibrium is constant. That's what we want. And of course, we need to remember that. All right, so I can write, so V is constant. That's what we need. Right. Okay, let me use different color, right? So V equals constant. And now I can add, okay, I should have left some space. Now I realize, so electric potential equals constant. That's what we need, and we are going to use it from time to time, so we need to remember that electric potential inside of the conductor in the electrostatic equilibrium is constant. Right. Okay, so that's what we need, and just small additional piece of information. Now, what can you say about the surface of this conductor? Anything interesting about that surface based on the recent results? Since electric potential is constant everywhere inside, and of course it will be on the surface as well. So how do we call surfaces at the same, or points which are at the same electric potential? Those surfaces are called equipotential surfaces. So any surface over conductor, any surface over charged conductor, right, is an equipotential surface. Right? Equipotential surface. Right. Okay. I can also add that. So this is equipotential surface. Right. All the time. But of course, in electrostatic equilibrium. So if you wait it long enough, long enough to make sure that the capacitor, the conductor reaches electrostatic equilibrium. Okay, good. So now that's what we need. And now, before we start discussing problem, which I like, we need to make a few preliminary steps. Okay, I will put a new bullet. And let's plot electric field, how electric field changes with distance. Let's assume that we have a charged sphere, metal sphere. And I want to plot how electric field changes with position and how electric potential changes with the distance from the center of the metal sphere. Right? Because again, we will need that in our problem. And that problem is in your homework. Right, so let me write which way I wrote solid charged metal sphere. Solid charged metal sphere. Right. Okay, I can even draw some small sphere. Right. Let's say of radius r. Right. And let's assume for simplicity, let's say, not simplicity, just let's assume it's positively charged. And of course, any excess charge can be on the surface. Right. And now I want to plot first electric field versus R, and let's say this is R capital. And then I want to plot the electric potential versus R, and that is also, let's say, R radius. Again, it's a solid sphere. So let's start with the electric field. So what can you say about the electric field inside of the conductor? Again, in electrostatic equilibrium, of course, it is 0. So if we plot it, first it's going to be like this, in this part, the plot. Right, then outside, we've done similar problems in the past. Of course, you can use Gauss's law to find the expression for the electric field outside. And it will be, there will be over here a jump, and then it will decay as 1 over r squared. So this will be E equals k q over r squared. Right? So it looks like a electric field created by a point charge, right? By a point charge q. And it makes sense because of the spherical symmetry. Okay, now I want to plot also the electric potential. Okay, what can we say about the electric potential inside of the conductor? It's constant. We just discussed it. So I can plot. So it will be some constant up to the surface of the conductor, right? And then now it's something new, which we have never written, but you should be able to guess. What will be the expression for the electric potential outside of the conductor? Since electric field behaves as a, it looks like an electric field created by a point charge, here we should have also electric potential, which looks like an expression for the electric potential of a point charge. And of course, you can prove it again using this bridge, right? You can use this expression and derive the expression for the electric potential. But of course, we're not going to do it. So outside, electric potential looks like an electric potential of created by a point charge, right? And it will decay as 1 over r. So it will be v. You know what? Let me write it here slightly. I will want to step away. So V equals K Q over R, right? Okay, like a point charge, like a point charge, like an electric potential of a point charge. Right. Okay, and now also, what will be this constant? Can we write the expression for this constant? Since this curve and this curve, they intersect over here, right? So of course, this constant is KQ over R capital, right? So this constant is over here, right? So it will be V equals KQ over R, right? Okay, so we need this for our problem. And now the problem itself. Okay, I hope you got why is it KQ over R. Because it's just this function at this point, KQ over R, and then function stays constant. So the problem is 2649. 2649. And because of this problem, I postponed the homework. I just realized that some recitation classes already discussed that problem, but some didn't. All right. Okay, so what do we have here? We have two metal spheres. Unfortunately, I have only one metal sphere, right? The second, I just found a ball, right? Different radii. All right, one is smaller, one is bigger. And first, let's assume that this smaller sphere is charged. This is not. So this is charged, this is not. Then, at some moment, we'll take a cord and connect these two spheres. Long cord connects these two spheres. So we need to answer the question, what will be the charge in this sphere after we connect them, and what will be the charge in this sphere? So initially, only one was charged. So we need to answer the question, what will be the charge in both of the spheres after we connect them? Okay? So let me drop this, and I already drew spheres at least. So we have, this has a radius R1. This has a radius R2. And what is given? What else is given? Okay, I will probably write here above. So let me write first two metal spheres. So radii R1 and R2. Then there is a charge Q1, and charge Q2 is 0 initially. Okay, and now let me write next to the on the picture. So, which way I wrote it? Okay, let me start over here. So, about this sphere. So, Q1, it's initial. It's given, Q1, right? So, it's everything related to this sphere. And then everything related to this sphere I will write over there. And so, what's initial information about this sphere? So, Q2 initial is 0. Now, what we need to find? We need to find the amount of charge here when we connect these two spheres with the long wire. So let's say it's a long wire. Of course, some charge will move to that sphere, we hope, right? So let's label the amount of charge on this sphere after they connected as Q1 prime, and that charge over there will be Q2 prime, right? So it will be Q1 prime. I think I label it final, yeah. Final, so that's what we need to find. And of course, Q2 prime, again, final. we need to find. Right? Okay, now, also, I want to write also the expressions for the electric potential of this sphere and that sphere before and after. Can we write that down? And that's why we need it. That's why I prepared this. Right? So before, when these two spheres were not connected, can we write the electric potential? We knew the charge Q1, we knew the radius, so we can use this V equals KQ over R to write an expression for the electric field inside of the sphere number 1. Right? So I can write, for example, here V1 will be equal K Q1 over R1. Okay, let me separate this. And then, can I write the expression for the electric potential, again, of this sphere, but now after we connect these two spheres? Radius we don't change, just the amount of charge will be different. Oh, here, this formula, right? So it will be Q1 prime. So now, final V1 prime, it will be equal K Q1 prime over R, it's prime, R1. And now let's do the same for the second sphere. Right. Okay, let me separate these guys. So this is for the first sphere, that is for the second, right? Okay, so V2, it will be equal K Q2 over R2. And of course, that is 0, because the charge is 0 initially. And now I want to write also final expression for the final electric potential of the second sphere. Just using, again, still the same formula. So V2 prime, it will be equal K Q2 prime over R2. Okay, so now we just wrote down formulas, physics, which given and what will be at the end. And now we need to discuss physics. I can even put the line sort of, okay. Now, obviously, we all understand if this sphere is charged and that sphere is not charged, when we connect them with a long wire, some amount of charge, let's assume that it was negatively charged, so we can talk about electrons running. So of course, some electrons will run to that sphere. The question is, how many? 100, 200,000, or all of these electrons will run, all of the charge will run to the second sphere. Of course, the question is, what is a stopping mechanism which will stop charges from running from this sphere to that sphere? What is the stopping mechanism?
Wouldn't it be equal unless there was some sort of resistance?
That's usually one of the answers which I usually hear, right, when we have normal classes, right, and I can usually bug everyone, right, so with my silly questions. Yeah, some students say, okay, equal. 50% will go there, 50% will stay here. Very like the socialistic distribution of wealth, right, of charges, right. Some people say, what else? Yeah, usually sort of like equal, right? There were some other ideas, right? Let's start from the fundamental point of view. Let's assume that, not assume. Okay, let's assume that we have an electron. And let me ask you a different question. When does, for example, this electron move? So any object, you know, will move only if you push it or drag it or kick it, right? So if it experiences the force, right? Of course, it only moves if it experiences the force. In this case, of course, if it experiences an electric force. So what does an electron must experience in order to experience this electric force? Of course, it must be exposed to the electric field, right? So, of course, there must be an electric field, of course, in the opposite direction in order to experience electric force. It's one approach, right? It's one approach. But if we try to use the idea of the electric field, what's the value of the electric field inside of the conductor? It's zero. And it's not going to give us any equations, right? 0 equals 0, it's nice, interesting, but we need some equations. So what else can be applied in order to justify the presence of the electric force and, of course, the motion of an electron? Recent quantities which we just introduced recently. There must be the electric potential difference. You remember in the previous recitation class we were stopping the electrons shooting, my neighbor shooting at me, right? That silly situation. And we were discussing what should be the potential difference, right? Should it be positive or negative in order to accelerate electron or decelerate electron? Exactly the same here, right? So there must be a potential difference so that electron will move. But what do we want? We want a slightly different situation. We have slightly different situation. We want to answer the question: when does electron stop moving? So, in order to stop moving, for electrons to stop moving, either electric field must be not either electric field must be equal to 0, and what can you say about the electric potential? The electric potential or potential difference, electric potential difference, delta V must be equal to 0, or V equals constant. So it means what? Charges stop moving from this sphere to that sphere when what? When the electric potential of this sphere will be equal to the electric potential of that sphere, so that the potential difference would be 0 between these spheres. Make sense? Again, I switched from the electric field because electric field is not going to give us an equation, right? So we need to have some expressions so we can use them to solve the problem. So that's why I moved to the idea of the electric potential. In another way of looking at this, more like a conceptual look. Before we connected these two spheres with a wire, we have isolated sphere, this, and that sphere was isolated. And of course, this was an electrostatic equilibrium, and that was an electrostatic equilibrium, right? So this was in the electrostatic equilibrium, and the electric potential was constant, right? Inside of the sphere, electrons get settled, they did their job, right? So electric field equals 0, electric potential is constant, and the same about that sphere. But now, once we connected these two spheres with the wire. What is a piece of wire? It's a piece of metal. For electrons, it's a gigantic piece of metal. And now we have this piece of metal soldered to this piece of metal, soldered to that piece of metal. So for electrons, now this whole structure now is a new gigantic solid piece of metal. And now once we connected them, all right, so now this solid piece of metal is not in the electrostatic equilibrium. So now all these electrons will wake up again. Okay, we have to run again. In order to make what? In order to make electric field 0 now in this new complicated piece of metal. And the electric potential must become constant. So the electrons now will wake up. Okay, now electric field again not 0. Electric potential is not constant. We have to start running to make electric field 0 and the electric potential constant. And they will keep running and running until electric potential everywhere will be the same, and of course electric field equals 0. But of course I explain electric field kind of doesn't give us an equation, so we have to discuss electric potential. Make sense? So the first piece of physics which we need to use in this problem that the electric potential must be equal. So this V1 prime must be equal to V2 prime, right? After we connect them, so that new electric potential must be constant, must be the same. Right, so let me write, so electrons will stop moving when V1 prime equals to V2 prime. So that's the first piece of physics which we have to use. And of course now we have the formulas, we have expressions, right? That's why I started with that. So I can write explicitly, so it will be K Q1 prime over R1 equals to K Q2 prime over R2. So that is equation number one. Of course, we can cancel K, right? But anyway, so that is equation number one. Okay, now let's think. Is it enough to solve the problem? So we have one equation. How many unknowns? We need to find Q1 prime, and we need to find Q2 prime. It's the amount of charge after we connect these two spheres, right? So one equation's two unknowns, not enough. So from a mathematical point of view, we cannot solve a system like this. So it means that we need to somehow find a second equation. Without the second equation, we wouldn't be able to solve this problem. So, and of course, now it must come from, I don't know, different physical idea, different concept. What else can be used over here in order to solve this problem? Something very fundamental. And we actually used that fundamental a couple of classes ago. And you used it in your exam, in one of your multiple choice questions. What else can be used? I'm sure that all of you know that concept, that idea, right? What else? I just need to guide you to the right place of your brain because you all know that. Look, let's just use some numbers, right? Let's assume that we have here 50 electrons, right? That's the extra amount of charge, right? Excess amount of charge, 50 electrons. So when we connect these two spheres, and let's say, for example, let's say 10 electrons will move to that sphere. So what will be the total amount of electrons in this sphere and in that sphere? Will be still 50, right? Because electrons cannot escape, so they are either here or there. If you add these electrons, excess of course electrons, plus those guys, those electrons, you must have exactly the same 50 electrons because they cannot escape. They are prisoners of these two spheres. They can be either there or here, right? So what can we use? Conservation of charge. Conservation of charge must be used. That's another fundamental piece of physics which can be used now. So now, second, conservation of charge. So it means what? Before we connected these two spheres with long wire, it's a Q1 plus Q2 must be equal to the total amount of charge after we connected them. Q1 prime plus Q2 prime. Right? So we can write, so Q1 plus Q2 equals to Q1 prime plus Q2 prime. And of course, we know that this amount of charge is 0, so we can simplify that. So now that will be the second equation. And now do we have enough equations? We have two unknowns still, Q1 prime and Q2 prime, because this is given. Two unknowns, two equations, physics is over. We used all the physical ideas. Now it's just algebra. You just need to solve a system of two equations with two unknowns. What can be easier than that? Everyone, any of you can solve this system. Right. Okay, so let me now do these calculations. Right. So probably I will probably solve this for Q2 prime first. Right. You know what, let me rewrite equation number 1 first. Equation number 1, R2, okay, let me write, so R2 Q1 prime equals to R1 Q2 prime. So I just take this denominator, multiply it, move it over there, and this denominator move to that side. And of course, K canceled. And the second equation, okay, as I said, I want to solve it for Q2 prime. So I can plug it in the first equation. Q2 prime equals to Q1 minus Q1 prime. And then I will take this Q2 prime and plug it into equation number 1, right? As a result, oops, wrong color. So as a result, this can be written as R2 Q1 prime equals to R1, and that different this difference Q1 minus Q1 prime. Wait, Q1 without prime, first one. Yeah. Q1 minus Q1 prime, right? Okay, so now one equation, one unknown, Q1 prime. So we just need to combine this and that term, right, on this side. So it will be R1 plus R2 Q1 prime equals to R1 Q1. Then, so the final push, Q1 prime is equal, will be equal Q1 prime equals to the ratio of this R1 and R1 plus R2 and times Q1. Right. So that's the answer for, that will be the amount of charge left in the first sphere, which was originally charged. And now you can plug this into the second equation. You can get Q2 prime. It will be exactly the same, but here you will have R2. So, and then from here, you will get Q2 prime equals to R2 divided by R1 plus R2 times Q1. So that will be the amount of charge in this second wire. And of course, you can play with the limits, right? If spheres are of the same size, then of course the amount of charge will be split 50-50, right? But of course, if this is, for example, like a point charge, R1 equals to 0, then the whole charge will just run away into that sphere. You can look at that limit. Or if this is R2 is basically point charge, R2 equals to 0, then the whole charge will just stay over here, right? Nothing will move. Right? So I like this problem because of the discussions. So what's the stopping mechanism, conservation of charge, right? But of course, when we have real classes in the classrooms, right? Of course, it's better. It's much, much better, right? Because I can shake students better, right? So I can get all these answers. Usually, I can get all these answers from students. Right? So exactly the same problem will be in your homework, but of course with numbers. But you know I don't like crunching numbers, right? I usually prefer to get in expressions, and then, right? If numbers are given, yeah, I can crunch it. But okay, all right. So that's what I wanted to discuss, right? Just because I like this problem. All right, and okay, if you have questions, go ahead. Otherwise, oh, we have only 10 minutes left. Okay, so next, capacitors. So now it's time to start introducing capacitors. Okay, I will erase this. Right. And as I said, now we'll start moving to simple circuits, right? And of course, guys from EE department, of course, you will go much deeper, right? But with you will learn different techniques, right, and so on. But we need to look at all this from the physical point of view, right? We will try to justify everything, explain all right, using the foundation which we introduced. And as the first element, let's introduce capacitance. Right. So capacitance, what is that? First of all, you all know that we have capacitors almost everywhere. Any circuit has tons of capacitors. So what's the role of a capacitor in a circuit? And again, usually when I ask this question to students, almost like every time, students give me the same answer. It's an element, it's a device which allows us to store, or a system which allows us to store charge. Absolutely correct. Nothing wrong with that, right? I will never tell that this is wrong. No, it's correct. But I want to present its role in a slightly different way. And I will explain why. And in my opinion, it's slightly deeper. Right? I want to present it in this way. The role of a capacitor, it's a device which allows us to store, but energy in the form of the electric field. Why I prefer in this way? Because in a month or so, when we will be in magnetism, we will introduce inductors. Lots of similarities between capacitors and inductors. And when we introduce inductors, I can introduce their role as it's a device which allows us to store, again, still energy, but now it will be in the form of the magnetic field. So capacitors store energy in the form of the electric field. Inductors will allow us to store energy in the form of the magnetic field. So their roles will be similar, right? But the role of this in the world of electricity, the role of this in the world of magnetism, but their roles are similar. So it's easier to juxtapose them and compare them. So it's different parts of physics are connected better if you present it in this way, right? So usually I present the role of a capacitor. It's a device which allows us to store energy in the form of the electric field, energy. And then you can use that energy, right, for example, in RC circuit and so on, right? Okay. And so now let's introduce definition. What is capacitance? So let's assume that we have two identical electrodes, basically two pieces of metal, right? So let's say this electrode, let's say this is charged with plus Q, this is charged with minus Q. Every time two electrodes has the same amount of charge, but one is negative, one is positive. Because how do we usually charge it? We just usually take, for example, let's say 100 electrons from this electrode and move them to over here. As a result, this will be positively charged, plus Q, and this will be negatively charged, minus Q. Because every time we just move some amount of electrons from one electrode to the other one. As a result, charge in absolute value must be the same. Right? Okay, then of course there will be some potential difference, since this is positively charged, right? So around that there will be positive electric potential, and this is negatively charged, so there will be negative electric potential around that. And of course, as a result, there will be potential difference delta V. Okay, and now let's start playing with these parameters, with Q and delta V. I think it's more or less obvious. If you, for example, increase the amount of charge, okay, increase this, decrease that, right? But increase an absolute value. What will be the potential difference, delta V? It will go up as well. You increase charge, potential difference goes up as well. You increase potential, or you increase charge more, potential difference will go up more. So they behave sort of in a similar way. So what about the ratio? Of course, normal response of any normal human being, right? So what about the ratio of Q and delta V if they grow together? Grow old together, right? Right. It's a normal question, right? And if you start playing with data, you will realize, you will see that if you take the ratio of charge versus potential difference, it will be the same number. Okay, with an experimental error. If you're getting the same number, if you don't change the system, right? It means what? It means that that number is some kind of intrinsic property of this system. If it's an intrinsic property, right, some special number, it might be useful. It might be useful, that number, right? So let's give a special name to that number, to that ratio, Q over delta V. And that's what capacitance is. Capacitance, C, is the ratio of charge versus potential difference. Just charge, Q, positive charge. Don't try to add or subtract charge. No, just Q divided by delta V. Absolute value of the charge of one of the electrodes. So that's what, by definition, capacitance. Because it's just exactly the same number. You take the ratio Q over delta V, and it doesn't matter what's the charge or what's the potential difference. The same number. It's something intrinsic to this system. So it makes sense to give a special name. C equals, I will put 3 lines by definition, Q divided by delta V. That's what capacitance is. That's what capacitance. Okay, now, so if we introduce a new quantity, of course it makes sense now, do we need a special unit? SI unit, right? Of course you can say no, but since it is used so often by technicians, electricians, right, by engineers, researchers, right? So if you don't introduce a special unit, those people will hate you because every time they will have to pronounce, let's say, I have 5 coulombs over volts, 10 coulombs over volts, I know, 10 times 10 to the power of minus 10 coulombs over volts. Every time pronouncing coulombs over volts is just so annoying. If you don't introduce a special unit, they will introduce the special unit, right? To simplify their life. It's just natural, right? The response of any normal human being. If something is used a lot, it makes sense to introduce the special unit. In this case, that unit is farad, right? So that people would be happier, right? In their research, in their engineering work. So, as a result, units farad. Damn it. So 1 farad F, okay, I can write farad. You know what, let me just, farad. So 1 farad is 1 coulomb over volts, All right, so that's the unit, and now yeah, we wouldn't be able to solve the problem which I planned. Right, so next, this is definition of capacitance in general. You can apply it to find capacitance of any system. Of course, the simplest one is the parallel plate capacitor. We will derive it. Then there are some something like spherical capacitors, like when we have one sphere and there's another sphere concentric, or cylindrical capacitor, or you can find capacitance of a piece of wire. Of course, it will be not that significant, right? But sometimes it can be painful, right? Capacitance of some diodes, right? Schottky diode, which I used in my research, right? It has some small parasitic capacitance, and the researchers try to suppress it as much as they can. You can find capacitance of me, right? Probably it will not be small, right, with my amount of fat, right? So any object has some amount of capacitance, and this can be used to find that capacitance. Right. But since we use all the time or very often parallel plate capacitor, let's find capacitance of a parallel plate capacitor. Right. So we just need to apply this formula. So we need to write something, we need to write some expression for charge, something for delta V, and see what we can get out of that ratio. Right. So let's apply it for a, okay, I will abbreviate, you remember, a PP capacitor, a parallel plate capacitor. Too much to write, so capacitor. Right. Okay. All right, it looks like I will have to do that in the lecture, right? I thought I will be able to introduce capacitance and derive a formula for a parallel plate capacitor. And actually, I was also planning to solve one problem. But okay, real life is slightly different than what I imagine. Right, so I will have to do it tomorrow in our lecture. Right. Okay, guys, so that's it for today, less than I prepared. But anyway, if you have any questions, go ahead. I'm here. Otherwise, if you have other classes, you can go. And then, of course, also in 4 or 5 minutes, I will also have to go to another class.